Okay, let's continue with our discussion about spherical mirrors. The second type of mirror is called a convex mirror, and it's still shaped like it's part of a sphere, but the reflecting surface is the side that bulges out, as you can see from this diagram. This is part of a sphere, and light comes in this way and gets reflected off that way. So it's what's called a convex mirror. Okay, it's the opposite of the concave mirror. Let's look at what a convex mirror is capable of doing. Still, we use the Snell's law of reflection. Imagine, first of all, the optical axis of the mirror, which of course passes through the optical center. Once again, the optical center is the center of that spherical reflecting surface, and we draw an axis passing through that point, passing through that optical center, and then this is called the optical axis. Now imagine we have beams coming in parallel to the optical axis. Okay, parallel to the optical axis. Let's look at this particular beam. It comes in like this, and because of the geometry of the system, if I draw a line starting from the optical center, which is the center of the sphere, passing through that point where the incoming beam hits the surface of the mirror, that of course is the normal line. Okay, that's the normal line because this radius is perpendicular to the local surface orientation of the mirror, and this angle theta is the angle of incidence. Now, according to the Snell's law of reflection, the reflected beam would make the same angle theta. With the normal line as the incident angle. In other words, this angle is also theta. Okay. Now, you can imagine a beam coming like this. It gets reflected that way. Another beam coming in, say another beam coming in like this. It's going to get reflected that way. Okay, it's going to get reflected that way. And the beams, and this particular beam will get reflected like this, and that one will get reflected like that, and so on. Okay, so you see, of course, the beam in the middle simply gets reflected right back. Now, suppose you put your eye here. What do you see? Your eye will see reflected beams this way, this way, this way, this way, and this way, right? And these beams, obviously, will never converge on this side because they diverge, you can see. Okay, but to your eye, what do they look like? Well, they appear to come from somewhere behind. They appear to come from somewhere behind the mirror. Of course, there is nothing really behind the mirror. It's supposed to be totally dark. So there's no light at that particular point, but that point seems to be the point where all these light beams start from. So that if there is indeed such a point where all these parallel beams would seem to originate from after reflection, that would be a focal point, except it's what we call it a virtual focal point, but because no real light beams converge at this point, they just appear to start from there. Is there such a virtual focal point? Well, it turns out, just like the case of concave mirror, if you look at beams that are pretty close to the optical axis, in other words, this distance, okay, is far less than the radius. In other words, this angle theta is pretty small. Okay, this angle theta is pretty small. Then we can show that indeed there is a focal point, and that virtual focal point, and that virtual focal point is again located midway between the vertex point here and the optical center there. Okay, in other words, VF and FC are roughly equal to each other. They're roughly both equal to F over 2. I'm sorry, R over 2, R being the radius. Let's see how we can show that. First of all, look at this line and this line. They're parallel to each other, therefore this angle is also theta. Okay, this angle is also theta. But since these two angles are the same, we know that angle is also theta. Okay, so let's take a look at the this triangle. There's F, there's C, with this point which I call A. Okay, so look at the triangle ACF. Okay, ACF. These two angles are the same, so this is an isosceles triangle, which means this length is rough. It should be exactly equal to that length. Okay, exactly equal to that length. But wait a second, these angles are very small. Okay, theta is very close to 0. So AF and VF should be almost equal to each other in length. No, they don't look like that because I artificially put that A really high. This A should really be somewhere here, very, very close to the optical axis. So therefore, AF and VF are roughly the same. In other words, VF and FC are roughly the same. Therefore, indeed, all these beams, as long as they're close to the optical center, after getting reflected, they will all appear to emerge from a point F, which is midway between V and C. That is called a virtual focal point. Okay, virtual focal point. Given the idea of a virtual focal point, we're now able to draw the image of any object placed in front of a convex mirror. Okay, we have two rules to follow. One is, if I draw a line starting from the object aimed at the optical center, what's going to happen? Well, here's the optical center right there. Right? If I draw a line like this, you know, if I extend this line, it's going to go through the optical center, which means the normal line of this incident beam. Okay, the normal line of this incident beam is just the beam itself. So it's going to reflect it right back. Okay, that's rule number one. Just like the case of a convex, of a concave mirror, if you aim at the optical center or pass through the optical center, it goes right back. The beam goes right back. Okay, second rule is if I draw a line that is parallel to the optical axis, what's going to happen? Okay, parallel to the optical axis. There we go. Parallel to the optical axis. What happens is that after reflection, they appear to be originated from what? From the focal point. Okay, here's the focal point. So they appear to be from there. Appear to be from there. Okay. So here is a drawing of two light rays coming from the tip of our object. Okay, if you put your eye here, you see one beam going this way, one beam going that way. They appear to originate from where? From here. Okay, so this therefore is the location of the image of that tip. In fact, it's a virtual image because no light rays actually should be behind the mirror. So this is the virtual image formed by the mirror of this object. Okay, and it's a virtual image because no light goes behind the mirror, and it's upright. Okay, you can see here, and it's smaller than the original object, so it is virtual, upright, and magnified. Okay, ray diagrams for an object located anywhere on the optical axis in front of the mirror. Unlike the case of concave mirror, where the location of the object makes a difference, with the distance p makes a difference. With different p's, you can get images that are bigger or smaller, virtual or real, upside down or right side up, all kinds of differences. Here in the case of a convex mirror, I encourage you to draw diagrams for various values of p. Okay, greater than 2f, between 1 and 2f, and less than f. It turns out no matter how you draw it, there is only one type of image that you can form, and that is virtual, upright, and magnified. Okay, virtual, upright, and magnified. As a matter of fact, if a mirror is slightly curved outwards like that, slightly, okay, then you almost will get an image the same size as the object, but it's going to be a little bit smaller. Okay, so everything will be condensed a little bit. Can you think of a way to put this into a practical application? You get a mirror that's slightly curved out so that everything appears to be slightly smaller than the real thing. Well, the reason why you want to make them smaller is because that way you can have a bigger field of view. You can put more images. You can cram more images onto the same size mirror, right? And an example would be the rear view mirror on the passenger side of a vehicle. Okay, not on the driver's side, but on the passenger side. On the passenger side, if the driver looks at the reflection from that mirror, the mirror is slightly curved outward, so all the images will be a little bit smaller. That way, the driver can see more of the back side of the road. Okay, but there is, as you can see, there you probably recall, there is a line inscribed on the mirror. What does it say? Objects in this mirror are closer than they appear. Okay, now you understand why they say that? Well, it's because the images are actually smaller than they should be if you use a flat mirror. So they appear to be further away, but actually they're closer than they appear. That's why they say that. Okay, so again, the advantage is that you can cram more images, you can broaden your field of view at the expense of making everything look smaller than they should be. Okay, so that's the case of a convex mirror. And what about the mirror equation for a convex mirror? Well, I don't have time to derive it here, but if you were to derive it with the same idea of deriving for the case of a concave mirror, you will get the same exact expression for the mirror equation. 1 over f equals 1 over p plus 1 over q. Exactly the same as the case of a concave mirror, with one exception, one important exception. That is, to make this work, the value f has to be negative. Okay, what is f equal to? F still has the magnitude of r over 2. F is the distance between V and F, okay, the focal point and the vertex. But except that distance, of course, that distance is around half the radius. Except to make this work, to make this equation work, you have to attach a negative sign. Okay, so it's a lens. It's a mirror with negative focal length. And what does a negative focal length means is that it's a virtual focal point you're looking at. The focal point, in other words, is behind the mirror, on the other side of the mirror. Okay, for this reason, the convex mirror, occasionally we also call it a negative mirror because the focal length is negative. Alright, now that we looked at both concave and convex mirror, there is in fact one common case where both mirrors will actually become the same thing, and that is, what if r equals to infinity? You see, if r equals infinity, 1 over f goes to what? Goes to 0, right? You see, r goes to infinity, so f goes to infinity, 1 over f goes to 0. And what that means is that 1 over p plus 1 over q equals 0, whether it's a concave or convex mirror, it doesn't matter. See, when r goes to infinity, you have a flat mirror, right? You have a flat mirror, which is just otherwise known as a plane mirror. We already studied that before. Okay, so it says 1 over p plus 1 over q equals 0. In other words, p equals negative q. Okay, p equals negative q. So we have a flat surface, and according to the mirror equation, if you put an object here, this distance is p, you are going to get an image the same exact size as the object, and that is q, and p and q satisfy p equals negative q. Okay, what does a negative sign mean here? And negative sign means q is negative. P is positive, but q is negative. Negative means it's behind the mirror. It's on the wrong side of the mirror. Okay, and that exactly agrees with our prediction. You know, it's the same distance, and it's virtual because it's behind the mirror. Okay, and as far as size is concerned, you know, the magnification is always equal to q over p. Okay. The absolute value of the magnification is always q over p, and that equals 1. That tells you that the size of the image is the same size as the object. So everything makes sense when you look at that special case of a flat mirror.